Download this code from codegive.com, link in the description below. OK, let's dive into building a billion-scale fast vector similarity search system using NMSLIB, non-metric space library. This tutorial will cover the essential concepts, considerations, and a practical code example to get you started. Understanding the landscape. Before we jump into NMSLIB, let's clarify the challenges and options in similarity search at a large scale. What is vector similarity search? You have a collection of vectors, representing data points, images, documents, etc., and you want to find the vectors that are most similar to a given query vector. Similarity is typically defined using distance metrics like Euclidean distance, cosine similarity, or dot product. The curse of dimensionality. In high-dimensional spaces, the traditional nearest neighbor search becomes computationally expensive, or even impractical. This is because, in a high-dimensional space, most points are nearly equidistant from each other. Approximate nearest neighbors, and to overcome the curse of dimensionality, we use N algorithms. These algorithms trade off some accuracy for a significant speed-up in search. Instead of finding the absolute nearest neighbors, they find approximate nearest neighbors. Why NMSLIB? NMSLIB is a powerful C++ library with a Python interface that excels at large scale and search. It supports a wide variety of non-metric spaces and indexing methods, giving you flexibility to optimize for your specific data and requirements. 2. Key concepts: indexing and searching. At the core of an search is the idea of building an index. An index is a data structure that allows you to quickly narrow down the search space. 1. Indexing. You build an index on your dataset of vectors. This involves choosing an appropriate indexing algorithm and setting parameters that control the trade-off between index size, search speed, and accuracy. The choice of the indexing algorithm depends heavily on your data characteristics. Common choices in NMSLIB include hierarchical navigable small world, HNSW, one of the most popular algorithms for general purpose and search. It builds a multi-layer graph, where each layer represents a progressively coarser approximation of the dataset. It balances speed and accuracy well. ANOI, approximate nearest neighbors. Builds multiple random projection trees. Relatively simple to implement and often a good starting point. KD tree. A space partitioning data structure. Good for low-dimensional data but struggles as dimensionality increases. Neighborhood graph and tree, NGT, another graph-based method that performs well. 2. Searching. Once the index is built, you can query it with a query vector. The index efficiently narrows down the search to a subset of the data. The algorithm then calculates the distances between the query vector and the candidates from the narrowed down search space. The k nearest neighbors are returned as the result. 3. Choosing an indexing algorithm. Selecting the right indexing algorithm is crucial. Here are some considerations. Data dimensionality. HNSW is often a good choice for medium to high dimensions. Dataset size. Some algorithms scale better than others. HNSW is generally suitable for large datasets. Query time versus indexing time trade-off. Some algorithms are faster to build an index but slower to search, and vice versa. Accuracy versus speed trade-off. You can tune parameters to favor either higher accuracy or faster search. Data distribution. The distribution of your data can affect the performance of different algorithms. 4. Practical example with NMSLIB. Let's walk through a Python code example using NMSLIB and HNSW. Explanation. 1 Data generation * we create a sample dataset of random vectors. Important, replace this with your actual data. Convert your data to a number pi array of np.float32 type, as this is the preferred format for NMSLIB. To initialize the index *, we initialize an NMSLIB index. Method equals HNSW, we choose the HNSW indexing algorithm. Experiment with other methods like ANOI, NGT. Space equals L2, we specify the L2, Euclidean, distance as the similarity metric. Other options include cosine, dot product, and many others, depending on your needs. 3 Index the data *. Index.add data point batch, data, we add the data to the index. The add data point batch function is efficient for adding large amounts of data. Index.create index, index_params, we build the index using the specified parameters. M, the maximum number of outgoing connections in the graph. Higher values typically lead to better accuracy but require more memory and indexing time. A common starting point is 16. F construction, controls the index construction effort. Higher values typically lead to better accuracy but longer indexing time. A common starting point is 200. Post, apply post-processing to improve memory usage. 0 is off, 1 is on. 4 Query the index index.set query, query_params, we set query time parameters. F search, controls the search effort. Higher values typically lead to better accuracy but longer search time. A common starting point is 50 to 200. Index.knn query, k equals k, we perform the k nearest neighbor search. Query, the query vector. K, the number of nearest neighbors to retrieve. The function returns IDs, the indices of the nearest neighbors, and distances, the distances between the query vector and the neighbors. 5. Optional, save and load *. You can save the index to disk and load it later. This is useful for reusing the index without having to rebuild it every time. Scaling to a billion vectors. Now let's address the key challenges of scaling to a billion vectors. 1. Memory *. Quantization *. NMSLIB supports quantization. Quantization reduces the memory footprint of each vector by storing it with fewer bits. For example, you can use 8-bit or 4-bit quantization. This can significantly reduce memory usage at the cost of a slight decrease in accuracy. NMSLIB supports PQ, product quantization, and other quantization methods. Data sharding *. If the index becomes too large to fit in memory on a single machine, you can shard the data and the index across multiple machines. Each machine would be responsible for a subset of the data and would have its own NMSLIB index. A top-level search aggregator would collect results from each machine. This adds complexity to the architecture. 2. Indexing time *. Parallel indexing * use all available cores to parallelize the index construction. NMSLIB is multi-threaded. Incremental indexing * instead of rebuilding the entire index from scratch every time new data arrives, you can incrementally add new vectors to the existing index. HNSW supports incremental indexing to some extent, but performance can degrade after many insertions. Consider periodically rebuilding the index if the performance degrades too much. 3. Search speed *. Optimize parameters *. Carefully tune the parameters of the indexing algorithm, example M, F construction, F search. Use a validation set to evaluate the accuracy and speed for different parameter settings. Asterisk hardware acceleration asterisk consider using GPUs to accelerate the distance calculations. NMSLIB has some GPU support, but other libraries like FAIS are often more heavily optimized for GPUs. Asterisk distributed search asterisk if you have sharded your data and index across multiple machines, you can perform the search in parallel on each machine and then aggregate the results. 6. Code example with quantization. Explanation of quantization parameters asterisk. Asterisk train PQ, true, this enables the training of the product quantization codebook. The training step is essential to learn the optimal codebook for your data. It analyzes a subset of your data to build this codebook. Asterisk PQM, 16, this defines the number of subvectors. In this case, the 128-dimensional vectors will be divided into 16 subvectors of 8 dimensions each. PQM must divide the dimension of your vectors evenly. Asterisk PQB, 8, this defines the number of bits used to represent each subvector. 8 bits corresponds to byte-wise quantization, where each subvector component is represented by a single byte, 256 possible values. You could also use 4 bits for even greater compression. 7. Advanced considerations. Asterisk online learning asterisk for scenarios where data is constantly arriving, you might consider online learning techniques to adapt the index to the evolving data distribution. Asterisk benchmarking asterisk thoroughly benchmark different algorithms, parameter settings, and hardware configurations on a representative sample of your data. Use metrics like recall at k, the proportion of true nearest neighbors that are found within the top k results. Asterisk monitoring asterisk monitor the performance of your similarity search system in production to identify any degradation in accuracy or speed. Implement alerting mechanisms to detect anomalies. Asterisk A/B testing asterisk when making changes to your similarity search system, example switching algorithms, changing parameters, use A/B testing to compare the performance of the new configuration against the existing one. Asterisk other libraries asterisk while NMSLIB is a good choice, be aware of other libraries for and search, such as FAIS, Facebook AI Similarity Search, Annoy, Spotify, and SCANN, Google. Each library has its strengths and weaknesses. FAIS is well suited for GPU acceleration. 8. Summary of steps for building a billion-scale system. 1. Data preparation asterisk convert your data to NumPy arrays of NP.float32 type. 2. Algorithm selection asterisk choose an algorithm, start with HNSW. 3. Quantization asterisk apply quantization to reduce memory usage. 4. Parameter tuning asterisk carefully tune the parameters of the indexing algorithm and quantization method using a validation set. 5. Memory management asterisk if necessary, shard the data and index across multiple machines. 6. Parallelization asterisk use multi-threading to speed up index construction and search. 7. Benchmarking asterisk thoroughly benchmark your system. 8. Monitoring asterisk monitor performance in production. Remember that building a billion-scale similarity search system is an iterative process. You will need to experiment with different algorithms, parameters, and configurations to find the optimal solution for your specific data and requirements. Good luck.